Okay, so welcome back to solving wave equation using Leapfrog. In the last video, I showed you the derivation of Leapfrog, how we can prove that Leapfrog is equivalent to direct methods finite differencing for solving wave equation. So I'm going to recap that very quickly one more time. So this is the wave equation after we convert it into a system, where we need to deal with three variables, r, s, and u. R by definition is v du dx, and s is du dt, and u is the displacement. So the wave equation originally is based on u. We convert the second order differential equation to a first order system, and we discussed that to solve that we need to discretize these two equations at a half point in time and space. So we talked about the discretized version of these two, and then we wanted to prove that Leapfrog is equivalent to the direct method. So if we pick either of these two, which are the Leapfrog discretization of these two equations, if you pick one of these two, let's say we pick the second one, and then use the definition of S and R in here, then we can show that that's exactly equal to direct method. So let's look at this one more time. S is by definition du dt, and from here we can relate S at half time discretization and let's say spatial coordinate xj is equal to the central difference version of du dt, which is un plus 1 minus un divided by del t. We can do the same thing for r at j plus half, which is equal to v, and then define the central difference version of du dx. Now we can use these two in, let's say, the second equation here, which is the Leapfrog version of the second equation here. All right, so I'm going to plug in the definition of S and R into this second equation. So R Sj n plus half is equal to this. Sj n minus half, we just replace n by n minus 1. For these two, we're going to use this definition, where for j plus half we use this. For j minus a half, we replace j by j minus 1. So after plugging these four into these four terms, then we end up getting an equation like this, where everywhere we have u's and there's no r and s anymore. Okay, so now if you look carefully, you'll see that that's exactly the direct method discretization of second order differential equation in time, or differential or the second derivative of u with respect to time. And this term, or these three terms, imply the second derivative of u with respect to x. So that's exactly the wave equation discretized using central difference for t and r, t and x. And so that's exactly the direct method. So this proves that Leapfrog is equivalent to direct method. All right, so the last thing I want to quickly go over is the Lax-Wendroff version of the discretization of the wave equation. To remind you, to get the Lax-Wendroff, we can go to page 178, which I tabulated different schemes that we learned so far. So I'm going to go quickly to that page one more time. Here is page 178. And if you look at this table, at the bottom here we have the discretization of Lax-Wendroff. So all we do is just we plug in the u equation right here. And remember, for wave equation we have two equations, one for r and one for s. Basically three: one for r, one for s, and one for t. One for u. All right. So if we go to Lax-Wendroff scheme right here, so this is the discretization of advection equation for r. This is discretization of advection equation using s. Remember, we are using discretization on page 178. And this is just the centile difference in the time derivative of u, and then average of s for the spatial derivative. So basically this is du dt is equal to s at n plus half and j. So this is basically the equation we had right here. Or in other words, this is the equation for u. Okay. So 3 equations to solve, and the way we do this in Lax-Wendroff, you see that I kept all the n plus 1 variables on the left and all variables with n on the right. So everything is known from the first equation. On the right side, we get n plus 1, r at n plus 1. Then we use r at n plus 1 and s at n plus 1 into the last equation where we have n plus 1 here. Well, actually, rn plus 1 is not used here, but we can only use sn plus 1. So anyways, we march these 3 in time, and then for the next time step we have these variables, we can find the n plus 2 variables. Alright, so that's how we solve these 3 equations simultaneously. Now I'm going to show you 2 MATLAB scripts on implementation of direct method for solving the wave equation in 1 dimension and in 2 dimensions. Alright, so here is the script. I already posted on the website. The goal here is to solve the wave equation with reflective state boundary conditions. Alright, so what we do is we need to discretize our x and time axes. Let's say these are the discretizations. Initial time. I didn't put any final time because I'm just making an animation, and I put some limit on the animation or number of frames in the animations. But if you don't want to make an animation, then you have to have a final time point. Okay, so this is the minimum x, maximum x on the x-axis, my velocity, such that my alpha is less than 1 to satisfy CFL condition. This is number of frames to skip, the x vector, this is dx based on the difference between 2 successive x values. I calculate dt based on definition of alpha and dx over v. And as soon as I have dt, then with the number of time frames, then I can calculate the total or the final time. Based on the final time and initial time, I can discretize my time axis. I create the time-space grid using mesh grid. I initialize my displacement to 0, and I create the initial wave as the Heaviside function. So let's say we have a Heaviside function or step function. We want to see how it propagates with velocity v. Alright. So I'm assuming one-way traveling wave, and that's why I assign all the u's at time 1 to basically all the variables at time 2 with the shift in x. So let's say the variables from 1 to n minus 1 in x is going to show up in 2 to n in the next time step. So that's exactly how the wave is propagating from left to right, because I can easily say by looking at the x indices. Alright, so we created our initial wave, then we just apply our direct method, if you remember. So in direct method we had the central difference, so this piece is the central difference version of the derivative in time, and this one is the central difference version of derivative in space, and we multiply that by alpha squared. That's exactly what we had on the notes right here. So here's the derivative in time, alpha squared times delta squared. So this thing will be alpha squared, and then derivative in x using central difference, and that's what I have exactly here. Now let's look at boundary conditions, because these are I'm going from x index from 2 to n minus 1. And for the x index 1, I assign everything from x index 2 of the same time. So that means whatever it's time 2, it's going to be time 1. That means the derivative with respect to time is equal to 0, because these are at the same time point, let's say n plus 1. So derivative equal to 0 at x equals 0 means reflective, and for the right boundary I'm using a fixed end boundary conditions where I put the displacement equal to 0. The rest is just plotting in the x time axis, and the rest is the animation. We saw this from other codes for Leapfrog or Max Fredericks and things like that. Alright, so I'm going to run the code. So initially we get this step function, and the step function goes from left to right. It hits the, so this is the hard boundary where we put displacement equal to 0. This one is reflective, so when the wave hits there, it has to reflect back. And the reflection is, again, the wave is on the bottom. So if it was on the bottom, after reflection, it still is on the bottom. This one is different. It hits there, and then it goes on the top, because that's the hard boundary. This is the reverse boundary we talked about before. Again, when it hits, it gets flipped. You see that? Now it's on the bottom. But then when it hits this point, because that's reflective, it completely reflects back on the same side. Look at that one more time. There you go. So it's still on the bottom. But when it hits here, it's going to be reflected, well, flipped to the top side. So now you see the difference between two boundaries. The wiggles that we see here is the error associated with alpha, because our alpha is a bit less than 1, remember? So here's alpha. If you don't want to get these little errors, then the alpha should be exactly 1. Remember, direct method or leapfrog in this case is exactly accurate and doesn't have any numerical error if alpha is exactly equal to 1. By the way, alpha has to be less or equal than 1 to be stable, and you see that although alpha is less than 1, well, with alpha less than 1 you see some oscillations, but these oscillations never go in time. Alright, so I'm going to stop the code. The next thing is I want to show you the 2D version of the same code. So this is, well, maybe I need to talk about a little bit about other types of boundary conditions. So in this code, we can apply a reflective boundary on other points, like on XL. This is that I didn't use. This is the absorbing boundary. For absorbing boundary, whatever at time 2 will be assigned, whatever at x equal 2 will be assigned to x equal 1 and the next time point. So this is next time point, this is current. This is at x equal L, we can apply the same thing at x equal, that's x equals 0. If we want to apply that at x equal L, then everything at the next to the last point in x is going to be assigned to the last point in x at the next time point. So watch for the time index and the change in the x index. Alright, so let's move on to the 2D waves. In 2D wave, basically we follow the same thing, so I skip through most of the details. Now you have two variables to deal with. In the mesh grid, I only do the mesh grid in x and y. We don't put the time axis here. So now I create a cos wave in 2 dimension, half cos wave. Then I cut the rest of it using the Heaviside function, and then now to apply two wave traveling wave. Then I apply the boundary condition we had before using dudt equal to 0. Remember that? So that's in the notes where we discuss how we can create two-wave traveling wave as opposed to one-wave traveling wave, where we discussed that right here. So the difference between two-wave, one-wave, just on the second time step. So here's the second time step where we distinguish whether that's going to be two-wave or one-wave. Now, for the boundary conditions, now we have to do the 4 boundaries on the x and on the y, depending on whether you're on the left side or right side. And by the way, there's a typo here, I think these should be y. And that's why those are j indexes for y and I index for x. Alright, and then the central difference version in x, the central difference in y, and this is the central difference in time. So basically, that's the direct method using 2 dimensions. Now the rest is just for creating the video. So now let's see what happens if I run the code. So the video was posted on the web. Initially you get this half sine wave and then it propagates through the end. Watch this when it hits the boundary. Alright, so that was the discretization of wave equation using direct method. So stay tuned for the diffusion